So the next speaker will be an amazing speaker from Bar-Ilan University, because we are talking about, are we there yet? Why are we talking about are we there yet? Because popular media is announcing every few days that AI has finally solved language. But is it really so? If we look beyond the performance matrix, did deep learning really actually solve NLP? So, in this talk, we will hear about the remaining challenges in deep learning-based natural language processing. I would like to welcome to the stage the Shwartz Natural Language Processing Lab at Bar-Ilan University. Please give a big, big round of applause.
Thank you, and hello, everyone. So I'm going to talk about deep learning in NLP, and more specifically about the things that don't yet work. So a few words about me. I'm a PhD student at Bar-Ilan University in Israel, graduating very soon. I'm working on natural language processing, specifically focusing on lexical semantics, so the meaning of words. And I use deep learning in my work. If you ask popular media, then it looks like AI has already solved language. Here are a few examples. So Google solved one of the biggest language problems. Almost Human, Turing test, shut down AI that invented its own language. And I would actually like to start with 2 minutes of optimism. And I want to say that deep learning has advanced NLP dramatically over the last few years, thanks to some contributions that I'm going to mention next. So first of all, this is pretty trivial, but going deep. Adding more layers adds more power to the network. So according to the universal approximation theorem, feed-forward neural network with a single hidden layer can theoretically approximate any function. Now, of course, this is theoretical, and then in practice, it doesn't mean that you would necessarily find the exact network that approximates your function, but it is a good start, and we all know that language is complex, so this allows us approximating more complex functions. And it has been shown in several papers that the different layers of the neural networks capture different types of features. So starting from low-level features at the low layers, like syntactic features, and moving on to more higher-level features in the high layers with the semantic features. And this is also not very surprising, because it has been, something similar has been said before by computer vision people. So the second thing is representation learning. Let's look at an example task. This is named entity recognition, NER. In this task, the model is given some text, and it has to label each word in the sentence with the type of named entity, or none if it's not a named entity, like most words. For example, Kichiro Toyota decided to found Toyota in Japan in 1937. So Kichiro Toyota is a person, Toyota is an organization, Japan is a location, and 1937 is a time. All the other words are not named entities. So traditionally, in machine learning-based solutions, what we would do, we would take the text, we would extract some feature vector out of the text, and then we would feed this feature vector into a classifier. We would learn the feature weights, and the classifier would output the predictions. And this is what a feature vector can look like. So we may include the indices in some dictionary that we have of the target word, and maybe the surrounding words, and then maybe some binary features, like whether the word starts with a capital letter or not. So this is not really good, because it requires domain experts, and it doesn't scale if you switch to different domains. And if you look at NLP papers from the last few years, if you see the words feature engineering, it's almost always in a negative sentiment. We don't like engineering features anymore. Today, in deep learning, what we do instead is we feed the text directly into the model, and then we expect the model to learn both the parameters, but also the representation. And this is great, because theoretically, you could just get rid of the experts and save a lot of money. Instead of learning the representations from scratch, we usually start with some pre-trained representations. Specifically, we like to rely on distributional word embeddings. If you attended yesterday's talk by Navid, then you already know about word embeddings, but I'll just mention that briefly. So these are vectors representing words, and they are based on a linguistic hypothesis that basically says you should know a word by the company it keeps. So semantically similar words appear in similar contexts. For example, in September last year, in December last year, they would appear in the same sentences. And then this is just a part of a 2D projection of pre-trained word embeddings. So you can see that all the months are together. Well, you probably can't really see that. All the months are together, and all the numbers are together, and semantically similar words are embedded in proximity. NER with word embeddings would be something like this. We want to represent the target word, so we can concatenate the word embeddings of the target word and the previous word, the next word. In this case, found Toyota in. And we can hope that the classifier would learn that a word like found before the target word indicates that it's an organization. And then the nice thing about it is that during test time, if we see a new word like establish, which we haven't observed during training, it's going to have a similar feature vector to found Toyota in, because found and establish are similar words. So it allows for some generalization. But what happens now? I found Toyota keys. Did anyone lose them? This is a different sentence. It's exactly the same feature vector. We wouldn't want to classify Toyota as an organization here, because it actually refers to a specific car. So this is where recurrent neural networks, RNNs, come to the rescue. So in general, in NLP, we want to represent arbitrarily long sequences. So we don't know in advance how many words. And we also care about the word order. So RNNs, what they do, it's just a function that gets an input at each timestamp. Usually it would be a word. And it updates the internal memory and also outputs an output that captures all the semantics or everything related to the subsequence that it has seen so far. In this case, the output vector for Toyota would contain knowledge about I found Toyota. And if you use a bidirectional RNN, then it would also contain some information about the words after the target word. And this specifically would really help us here, because a word like clues, which is considered a long-range dependency, would help us disambiguate the word found and realize that it's actually about finding something and not about establishing something. So RNNs, and specifically LSTMs, long short-term memory networks, have been super useful for NLP. They're used in many applications. So does that mean that NLP is solved? No, it's not solved, obviously. And we're going to look at what's missing, some of the things that are missing. So let's start with a problem that I like to call the really big data problem. If you look at seemingly solved AI problems, not necessarily related to NLP, then ASR, facial recognition, machine translation, they work pretty well. But then if you look closer, then you see that actually ASR is only solved for American English, male speech with no background noise. And facial recognition only works well for white males. And machine translation works well for languages with a lot of data, like English and Spanish. But what happens when you don't have enough data? So if you try to train a model when you don't have enough data, you get the risk of overfitting. So basically, limited amount of training data, or training data in a very limited domain that comes with training a model with many parameters, which you would do if you train a deep learning model, can lead to overfitting. That means that your model is going to learn the very specific things in the patterns in the training set, while not being able to generalize for and solving the actual task. Here's an example. So what I did here is I used Google Translate, and I set it to Igbo, which is a language that I don't speak. And I just wrote I just typed I, which is definitely, I'm pretty sure doesn't mean anything in Igbo. And what I got back was a well-formed sentence in English that says, as it is written in the book of the law of Moses, which was in the wilderness, which was before the man who did the work of the kingdom of Israel. I'm pretty sure that's not what I wrote in Igbo. And you may have seen the headlines a few months ago saying that Google Translate is generating religious prophecies. So does that mean that Google Translate is religious? What does it mean? Yeah, so obviously Google Translate is not religious. What happened, well, I can guess what happened, is that Igbo English doesn't have a lot of data on the web. And the translation model was probably mostly based on translations of the Bible, which are available in almost any language. And then when it gets an output that's unexpected, something like I, then it just defaults to translating some biblical sentence. This is a really serious bug. Then sometimes when we don't have enough data, but we still want to train a model, we try to create it in a somewhat artificial way. That's also problematic. Let's look at the life cycle of most NLP data sets. So we'd start by, I need a large data set. I want to try to train a neural net on a very cool task. And then collecting data from experts is very costly and takes a lot of time. Then we try looking for shortcuts. Maybe we can crowdsource that, or maybe we can simplify the task. We don't need experts. And then when we publish our data, then people start training their deep learning models on the data. And at some point, they get better performance than humans, which is the time to be skeptical and ask ourselves whether something may be wrong with the data. Here's one example, the NLI task, natural language inference. The model sees two sentences, a premise, which is considered true, and a hypothesis that it needs to decide whether it's also true or not. So it's a three-way classification problem. Here's an example. Street performer is doing his act for kids. Then a person performing for children on the street would be entailed. It's correct. It's true also. A juggler entertaining a group of children on the street is neutral. We don't know. It may be, but we don't know for sure that the street performer is a juggler. And the magician performing for an audience in a nightclub is considered a contradiction because it describes a different event. If you're confused, it's OK. It is a very difficult task. It requires a lot of layers of knowledge, like about word meaning, syntactic structure, ability to resolve references. So you need to know that he refers to the street performer, word knowledge, common sense reasoning, you name it. Many different types of knowledge. And a few years ago, there was a new data set from Stanford that contains 500,000 examples, as opposed to just a few hundreds in the older data sets. And they based it on image captions. So the premises are just image captions, sentences like this, two dogs running on grass. And then they just gave crowdsourcing workers the premises and asked them to generate sentences with all the three labels. So they would come out with things like two cats running on grass, it's a contradiction. Two dogs run outside is an entailment, and a white dog and a brown dog are running on grass. We don't know for sure the colors of the dogs because they don't see the images. So since its publication, there were a lot of people starting to work on this task or going back to work on this task. The number of parameters in the model was growing rapidly. This is not moving anymore. Oh, sorry. So the number of parameters in the models was growing rapidly, and with that also the accuracy. And at some point, the best performance was better than humans. So this followed with a line of work showing that the task is not actually solved, the data set is solved, which is different. So one line of work showed that if you train a model to only look at the hypothesis, then it does much better, it performs much better than chance, which is what we would expect it. We would expect it to perform like chance. So this is due to the way that people generated the sentences. So here are a few examples. For entailment, they generated very general sentences, like a person is doing something. This is almost always true. Or to create a contradiction, then they replaced some words with nobody or some other negation. And this is where I found this really funny. It's very specific to this data set. Since the premises are taken from image captions, then there are a lot of dog images. So the workers somehow decided that what contradicts dog is a cat. So if you see the word cat in the hypothesis, it's almost always a contradiction. And in another line of work, including one paper from ours, so we showed that the state-of-the-art models that are trained on this data set, they actually confuse word similarity with entailment. So I'll give an example. I'm not sure it's clear. So a man is holding a saxophone and a man is holding a guitar are two different sentences, but the model will consider them as saying the same thing because saxophone and guitar are embedded in proximity in the embedding space. And this leads me exactly to the next point, which is we base our models on shaky ground of distributional similarity. So I actually like word embeddings. I use them a lot, but they have some problems. I'm going to mention a few of them. So first of all, words in English tend to have more than one meaning. And then in word embeddings, they have a single vector. So something like mouse, for example, it has the meaning of a computer device. It also has the meaning of an animal, maybe also Mickey Mouse. But if you look at the nearest neighbors of the vector of mouse, then you're going to get only words related to its computer device meaning. And in other words, you're going to see maybe a mix of the different senses, which is also not good. The second problem is that word similarity is defined very vaguely. What do we want when we ask for similar words? So, for example, if I look for the similar words to cat, then I'm going to get the plural form cats, which is good. I'm going to get a type of cat, kitten, then other pets like dog, beagle, puppy, and category of cat, feline, and pet. And this is very confusing because it's all mixed together, and we don't have a really straightforward way to tell how these words are similar, in what way are these words similar to cat. And this is something that I personally work on. And another problem with word embeddings is representing multi-word expressions. So we don't necessarily want to combine the different word embeddings to get some new meaning, because something like named entities like New York or WeAreDevelopers is not exactly the same meaning as the meanings of its words. It also happens with verb and particle. So for example, carry on is not the same as carry, and keep calm is not the same as keep. And with adjectives, so for example, a black cat is both black and a cat. A good driver is a driver, but it's not good in general. It's just a good driver. And fake news is not clearly news at all. And again, we don't have a good way to separate these cases. And in noun compounds, so crocodile tears has nothing to do with crocodile. And olive oil is derived from the meaning of olive and oil, but in a different way from baby oil. This is also something I worked on. OK, so we talked about multi-word expressions. So now if we want to move beyond the word level, maybe we want to represent sentences. So can we embed a sentence into a vector? It depends who you ask. This is a very famous quote from Ray Mooney. He said, you can't cram the meaning of a whole sentence into a single vector. And recently, there was a paper from Facebook showing that actually you can do that. And if you do that, you're going to get a vector that captures some interesting linguistic properties. So just to explain what I mean by sentence embedding, here's an example for a few examples for sentence embedding methods. So the autoencoder encodes a sentence with a recursive neural network, outputting a vector. And at training time, the objective is that there is a decoder that tries to reproduce the words from the vector. So then the vector must capture the essence of the meaning in order to succeed in reproducing the words. Similarly, the skip thoughts embedding does the same, but tries to predict the surrounding words, the surrounding sentences. And you can always just train a model for a downstream task like machine translation, and then use the intermediate representation as general purpose sentence embeddings. So the paper from Facebook showed that sentence embedding generally capture the number of words in the sentence, whether a specific word is in the sentence or not, word order, and so on. But I would like to show you a few things that there's just no way that they capture. So implicit meaning, if I say something like, I didn't eat anything since the morning, then it means that I'm hungry, but it's not there in the sentence. Broad context, if I say no thanks, then I might mean something like I refuse to your offer of food, if you just offered me food. Non-literal meaning, so I could eat a horse doesn't actually mean that I'm going to eat a horse, it just means that I'm really hungry. And pragmatics, do you have some food here? I don't just expect a yes-no answer, I expect to get some food. And common background, if I say something like there's a new restaurant in the city, I probably mean in Vienna. And that's, unless you're American, and the city sometimes just means specific city. OK, another problem unrelated to that is that our models are not robust enough. So maybe some of you know this comics from XKCD. It says, this is your machine learning system. Yep, you pour the data into the big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just steer the pile until they start looking right. Sadly, this is too similar to the way that we develop NLP models in the last few years. There's just too many hyperparameters that we need to tune. Here are a few examples. And sometimes the values of these hyperparameters, they make the difference between a non-working model and the new state of the art. And this is problematic because if you want to reproduce somebody's model, write it, for example, in a different framework, a different programming language, it's very difficult to do that. Even if you run it on a different data set, you're not guaranteed to get good performance. And finally, this is the last problem and one of the biggest problems, the lack of interpretability. So when we trained machine learning models before deep learning, then we knew exactly what goes inside because we designed the features. And today what we do is we just train black box models. So we send our input into some pile of linear algebra, and then it just outputs something, and we don't know what happened inside. And this is really makes it really difficult to answer questions like, why isn't my model doing what it's supposed to? Or how do I debug my model? And not less importantly, can my model explain its decision? So related to that is the problem of biased models, fairness in general. Maybe you've heard this news story a few months ago. Amazon built an AI tool to hire people, but had to shut it down because it was discriminating against women. So let's try to think what really happened here and how it relates to the lack of interpretability. So some things that could go wrong. First of all, our supervision is sometimes biased on its own. So what Amazon tried to do, what we would like to do, for example, is to predict whether someone is going to be good at the job or not. But we don't actually have the supervision for that. We have the supervision for previous decisions about people, whether they should be hired or not. And these decisions were made by people, and people are biased. So it could be that the person that made the decision in the first place thought that maybe men would be better qualified for this job. And then the model just learns to imitate this bias. And another possibility is that the dataset didn't contain enough women. There's also bias in the word embeddings in our input representations. Again, yesterday's talk by Navid talked about it in depth. Sorry. So, for example, something like men would be closer to programmer in the embedding space, and women would be closer to homemaker. And these biases are amplified in our models. And finally, the lack of interpretability makes it almost impossible to try to understand what makes the model say yes to one candidate and no to another, and sometimes it's going to be more correlated with gender. So the solution for that would be, first of all, don't include sensitive features like gender, but that doesn't really solve the problem because it's correlated with many other features. It could be correlated, for example, with writing style. And another solution is to try to actively remove these sensitive features. It's called adversarial training. So it's a really nice solution. If you represent a candidate using some feature vector X, and then your primary goal is to train a classifier F that predicts whether this person should be hired for the job or not. And you jointly train a classifier G that tries to predict gender. That's the adversarial. And then you make F forget what G learned. So basically, you get a classifier F that doesn't know anything about gender, so it can't really use this information for the classification. This is really nice, but again, be aware, there was a very recent work showed that it doesn't completely remove the feature, so it's not completely reliable. OK, so to sum up, deep learning has really advanced NLP in the last few years. It has been great, but we need to keep thinking about keep in mind the problems. We need a lot of data, otherwise we risk overfitting. We mess around with artificial data, and then we think that some task is solved, but it's not actually solved. We base our models on a very fuzzy definition of word similarity, and we don't have good representations beyond the word level. And finally, our models are not robust enough, and they're not interpretable enough. Thank you.
Thank you, Vered. My mic is not working. There we go. Thank you, Vered. I think we have time for questions. So let's see. And if you have forgotten, please don't forget to ask your questions via Slido. Use the hashtag AIC18. This is the white box stage. And then ask your questions away and also upvote the ones that you want to get asked. So right now, the highest ranking question is, are your slides online?
Not yet, but they will be.
OK.
Just search my name in Google. I will upload it to my website.
Exactly. And your name is Vered Shwartz. Yeah?
Yeah.
OK. The next question. Aren't n-gram word representation help to train models with word combinations?
They are. It's not good enough because of many reasons. First of all, they're not as common as single words in the corpus, in the text collection, so it's very hard to train a good representation for that. And also, many things are non-compositional. So I gave the example of crocodile tears. It has nothing to do with oh, sorry, no, n-gram solved that. No, it's mainly that it's not enough common. I would love to chat later with the person that asked this question. I have a lot to say about that.
Definitely. I mean, and also, please remember that we won't have time to cover all the questions, but we will be here. So the speaker will be here near the stage. So after the talk, you can also come up to her and ask questions. So next up, how can a machine learn to detect offensive language? Vocabulary usually changes over time, or people try to use escape characters, like, for example, at for A.
It's a good question. I didn't work on that specifically. I guess that you could just, as always, gather a lot of data and try to train a classifier on some encoding of the text, like using, for example, a BILSTM. I don't have a good solution for changing over time, except collecting new data. Sometimes maybe you can also use, if you use, for example, social media posts, then you can also use the responses to try to detect whether the original post was offensive. But yeah, I don't have a good solution for that.
OK. All right, then the next question. Humans also have to learn non-literal meanings of phrases. Can't we train a neural network to do so by giving examples?
If you have, whoever asked that, if you have a good idea on how to do that, please talk to me. This is a task that I'm fascinated about. It's difficult. Also, as a non-native speaker of English, I try to think, how did I learn these phrases in the first place? And sometimes you understand that from the context. Sometimes you understand that from trying to extract something from the literal meaning, like, I don't know, crocodile tears specifically, something that was originally because there's some story about crocodiles crying when they eat their prey. So there are many ways to do that. I don't know a very successful way to do that yet.
OK, so if you have asked that question, please make sure to come later to the stage and ask away. OK, let's do one more question. What's your recommendation for building semantics to overcome the problem of the fuzzy definition of similarity?
OK, so I think it's task dependent. I worked on a model that distinguishes between the different semantic relations. So you give it 2 words, and it tells you whether these 2 words are synonyms or whether one of them is more specific than the other. Maybe they contradict each other. All these things are considered very similar in word embeddings, but you need to actually train a model to find out whether they are, what's the exact relation. And very often what helps is looking at joint occurrences of these words in a large text collection. And sometimes they have these patterns that connect them that somehow indicate what's the specific relation between them, like animals such as cats. It means that cat is an animal.
Perfect. OK, so that's it for now. We will regroup again at 1:45. Please give a big round of applause to Berit Shwartz.